Steady-state photocapacitance, SSPC for short, is an optoelectronic method to study defects in semiconductors. The method makes use of the fact that defects can trap charge carriers and that these carriers can be emitted by absorbing photons with a specific energy. By finding the photon energy necessary to make the defect emit a charge carrier, we can localize the defect energy level in the semiconductor's bandgap, which helps us to identify what the defect's microscopic origin actually is. Unlike in thermal methods such as deep-level transient spectroscopy, where the carriers are emitted thermally, which limits the range of accessible trap energies, SSPC can probe the entire bandgap of semiconductors. So, in order for SSPC to work on a material, you need a rectifying contact, most often achieved by depositing a suitable metal on your semiconductor, so a Schottky contact or a Schottky diode. When you have your diode ready, you typically cool it down to low enough temperatures so that thermal emission from defects is strongly suppressed. Then you apply a reverse bias to the contact to increase the semiconductor volume that is probed. And then you illuminate the sample with monochromatic light to ionize one defect species at a time, starting at the lowest photon energy and going up to just below bandgap energy. And what we monitor during this illumination is the capacitance of the diode, because that provides a measure of the occupancy of defects. So if you have emission from a defect at a specific photon energy, you'll see it as a step in the capacitance you measure, with the height of this step being related to the concentration of the defect. And to ensure that we ionize each defect species completely, that is, achieving a steady state, we illuminate for several minutes at each photon energy. So all in all, what you get out of this method is a spectrum of capacitance versus photon energy that can provide an overview of the defects present in the semiconductor throughout the entire bandgap and their concentration. Our SSPC setup is located in a vacuum chamber that can be cooled down to 30 Kelvin by a closed-cycle helium refrigerator. The light source is a laser-driven plasma lamp emitting in a broad spectral range between 0.5 electron volts and 6.5 electron volts. The light is sent through a monochromator and then directed onto the sample through a window in the vacuum chamber. We record the diode capacitance with a high precision capacitance meter that simultaneously keeps the diode under a constant reverse bias. The method is capable of resolving defect concentrations on the order of 1% of the free carrier density. What is a bit special about our SSPC setup is that it is connected to one of the beamlines of our ion implanter. This enables us to perform implantations on samples mounted to the sample holder and then run SSPC measurements before and after without breaking vacuum or even bringing the sample back to room temperature. And this is pretty cool. I am currently running experiments here on electron-irradiated beta gallium oxide, which is, among other things, a promising material for use in power electronics. And to that end, control over defect population is vital, because even the smallest amount of defects can determine if a device works or not. So we are looking at intrinsic defects, which were created by low and high energy electron beams. And currently not much is known about the energetic position of intrinsic defects in gallium oxide. And in contrast to impurity-related defects, the formation of these intrinsic defects cannot be suppressed completely. So learning what their properties are and how they impact the material is important for designing good devices.